We are now going to derive the backpropagation algorithm for a multi-layer perceptron. There are two tools that we're going to use for this derivation: gradient descent and the chain rule from calculus. Gradient descent is an algorithm for minimizing an energy function, E, by iteratively updating the input to the function by moving the previous input in the direction of greatest decrease of the function, the negative of the gradient, by some step size, gamma. The chain rule states that the derivative of a function, f of a variable u, with respect to another variable, x, is simply the derivative of that function with respect to u times the derivative of u with respect to x. And we can repeat this process iteratively if u is also a function of x, or if u is a function of x. So to go back to our original problem, we have the multi-layer perceptron, and we want to find good weights for both the output and the hidden layer that improve the performance of the network overall. So first, we should observe that we can write down the behavior of the network as a function of the input. Yj is equal to a weighted sum of the input, and the output is a weighted sum of the hidden layers, the hidden layer nodes Yj. It's also important to note that the hidden layer of the network must have a nonlinear transfer function. It's the case that for any network of any depth that uses only linear transfer functions is exactly equivalent to a one-layer neural network. So if we're going to learn any meaningful features, we need to include some nonlinearity function in the hidden layer, at least. Next, if we want to improve the performance of the network, we can see that it is really a static function of the inputs, x. And if we want to change the performance of the network, then we need to change the weights. Can you think of how we might do that? Well, the answer is through optimization, or at least an answer is through optimization. So now let's step through how to do this, starting with a very simple example. In the first case, we're going to have a linear network, a linear regression network, where the output of the network is simply the weighted sum of the inputs. So we multiply input x1 by weight 1, input element x2 by weight 2. We define our energy or error function, and I'll use the two terms interchangeably, by half the square of the error between the predicted output y and the target output t. So let's step through now how to do gradient descent on this network, on this error function, to modify or to find the optimal weights for this network. So first, we take the energy function and we expand out the value of the parameter y to just explicitly be the weighted sum of the inputs. Next, we take the derivative with respect to weight 1, and we're going to do weight 1 first. And we see that the derivative of the error function, the exponent comes down, cancels out the half, and then it's simply the weighted sum in the inside of the parentheses, and then we take the derivative of this function, of the weighted sum, and with respect to weight 1, that derivative is simply x1. And then, just to tidy things up a bit, we rewrite this as the output of the network minus the target times the input x1. To make the actual weight update rule, we multiply it by the negative learning rate, which makes this a proper gradient descent algorithm. And again, just for tidying things, we will take the negative inside, and we see that the weight update rule for weight 1 is simply gamma times the target minus the output, or the error between the two, times the input x1. And the weight update rule for the second weight by symmetry is just the same thing, but it's input x2 instead of x1. And this should look familiar to you, because this is pretty much the perceptron learning rule that we learned. And now we see what is the mathematical justification for multiplying, updating the weights with the multiplication of the error times the input. Now, if we want to consider a more complicated case, we'll add the nonlinear function g to the network. So now the output y of the network is the squashed sum of the input weights. And we will interchangeably write this sum as explicitly x1 w1 times x2 weight 2, or just abbreviate it with a. The energy function, or the error function, is the same as it was before. And now we're simply going to step through this process again. So again, the derivation, we start with the energy function. We explicitly write out what y is. We use the chain rule to compute what the derivative of the error function is with respect to weight 1. And again, the exponent goes away. And this time, we're taking the derivative of this function of weight 1. So now it's, instead of it being the error between the output and the target times the input, it's the error between the output of the network and the target times the derivative of the nonlinearity of the output function times x1. And this again is the explicit application of the chain rule, taking the derivative with respect to weight 1. Again, to tidy things up, we'll just write it as y minus t, and then the gradient of A, the activity of the neurons coming in, times the input x1, to transform this into the gradient update step. On the weight 1 value, we multiply by the negative learning rate, and again we just do the algebra to tidy it up, and by symmetry we can derive the same thing for weight 2. Again, the only major difference in this case being this x2 term at the end. So now we have to answer the question of what is the derivative of the transfer function. And what we're going to see is why the sigmoid activation function was such a popular choice. The sigmoid function is a nonlinear function. It squashes the output to be between 0 and 1. And to get the derivative of this, because we need the derivative of g to compute the gradient update, we simply use the quotient rule from calculus. And we see that the gradient of the sigmoid function is e to the minus a over 1 plus e to the minus a squared. Now this is a little bit of a pain, because now when we're doing the backprop algorithm, or we're going to be doing the backprop algorithm, we need to keep around this gradient function, this gradient of the activity of the neuron, in addition to the activity of the neurons in the network. So we'd like to know if there's anything we could do to make this a little simpler. Well, there is. I'm sure you'll be surprised to learn. The sigmoid has a very nifty property, that if we step through these algebraic steps, we'll see that we can expand the denominator, expand the square out. We can then rewrite this as two fractions, 1 over 1 plus e to the minus a times e to the minus a over 1 plus 1 times e to the minus a. This first term here is simply the sigmoid function, so we can rewrite it as such. And then we want to ask if there's anything we can do with this term, the e to the minus a over the 1 plus e to the minus a. And there in fact is. We can add 0 to the numerator by first adding and then subtracting 1. We can recognize that there are two fractions here, that this is the difference of two fractions. One is 1 plus e to the minus a over 1 plus e to the minus a, which becomes 1. And then the remainder is just 1 over 1 plus e to the minus a. And this is just the sigmoid function again. And so we can write the gradient of the sigmoid as the sigmoid times 1 minus the sigmoid, or the derivative, I should say, at any point in the input space A. And so we can now write our gradient descent rule for the weight update. For weight I in this simple one-layer nonlinear network is the learning rate gamma. The change in the weight is the learning rate gamma times the error times the gradient of the transfer function times x1. Exploiting the fact that we know that g is a sigmoid function, we can rewrite this with the expansion we just made, or simply we can write it as gamma times the target minus the activity of the neuron times the activity times 1 minus the activity times x1. And this is a handy way of writing this out, because we don't need any special evaluations, or we only need to evaluate y once to get all these quantities if we're going to compute the gradient, and we don't need to have a special function in addition to the actual transfer function to compute the gradient update. So this makes things a little bit simpler. So now we're ready to tackle a multi-layer network. The result we've just derived will give us an update rule for the output layer, that is, the weights that map the hidden layer activity to the output of the network. But what do we do about the input? Well, we set up the error function as we did for the single layer case, but how do we find the derivative of the error function with respect to the input weight? That is to say, how does this error function change as we change these input weights here? Well, the answer is we apply the chain rule once again. Now we see that the derivative of the error function is the error signal times the derivative of the transfer function times the derivative of the term bk, which is just the weighted sum of the hidden layer activities, with respect to weight ij, which is just the derivative of the activity of the hidden node j with respect to weight ij, again, which gives us this derivative. We see the g prime function and then the input xi. And to get the weight update rule, we once again multiply by a -1 in the learning rate, and this is the same learning rate that is used on the output layer. And this gives us the number we add to weight ij to update it after presenting the current input x. So now we've seen the weight update rule for the output layer, and we've seen it for the hidden layers. And we can notice something interesting in these two rules. The weight correction computed at the output layer is propagated back in part through the weight matrix to produce the weight update at the hidden layer, and this is where the name backpropagation comes from. And we can continually apply the chain rule to networks of arbitrary depth, although we will see in the next lecture that there are some practical considerations that we will have to deal with. But if there was if x, instead of being the input, was another layer of neurons, we would simply then replace this x with the weight that maps it into x, and then the function of the transfer function x, and we would just iterate this process over and over again. So we should ask ourselves if this is always going to work. This is an optimization process, and optimization routines can get stuck in local optima, like here at the point marked WA. The initial position of the in the space of network weights can determine if you converge and how quickly the algorithm can converge. So if you start at WC, you should converge to this optimum right here. But if you start over at this location, you will probably end up in this weight A state. And this was a concern in the original paper. To quote from Rummelhart, Hinton, and Williams, they say, the most obvious drawback of the learning procedure is that the error surface may contain local minima, so that gradient descent is not guaranteed to find a global minimum. However, experience with many tasks shows that the network very rarely gets stuck in poor local minima that are significantly worse than the global minimum. We have only encountered this undesirable behavior in networks that have just enough connections to perform the task. Adding a few more connections creates extra dimensions in weight space, and these dimensions provide paths around the barriers that create poor local minima in lower dimensional subspaces. However, despite this word of hope that we can escape minima through the addition of extra neurons, we do still need to be cautious when we're training neural networks. If we keep adding neurons, as suggested in the previous slide, there is the risk of overfitting, as we discussed in the previous lecture. And second, a more recent discovery is that very high dimensional spaces, not only can you get stuck in local optima, but optimization routines can also get stuck in saddle node points they can also be very difficult to get out of, which in low dimensional spaces they're actually quite easy to get out of. And this was a counterintuitive result that came out in 2014. Additionally, the shape of your error function is also dependent on the data points that you include in your training set. And depending on your choice of training data, you can make optimization easy to find a solution, but it might not generalize well for the data not included in the training set. And that's why it's important when you're picking your training data to make sure you have sampled widely over the domain of the function that you're trying to learn with your neural network. And finally, the optimization routine is sensitive to the choice of learning rate. And next, we will describe some tips and tricks for doing backpropagation and hopefully to mitigate some of these concerns.